In the absence of a net force acting on an object, it will glide with constant speed in a straight line. At constant speed, the position of an object, x, is given by speed times time plus the starting position, x0. This is an example of a linear relationship where x changes linearly with the time. Linear relationships may be represented as straight lines on a graph. If position is plotted on the vertical axis and time is plotted on the horizontal axis, we may compare with the slope-intercept form of the equation of a straight line, that is, y equals mx plus b. M is the slope and b is the y-intercept. Here the slope represents the velocity or rate of change of position. 2 points are enough to uniquely determine the slope and intercept. The velocity of this graph is the slope and is found from the rise over the run, or the difference in x values divided by the difference in the corresponding time values. In this lab, the object in motion will be a cart on a track. First, make sure that your cart has decent bearings so that frictional forces don't become a large issue. Then approximately level the track. There's a screw at the end stop to adjust the level. Check the level by noting that the cart moves similarly in both directions. Be careful not to aim the plunger on the cart such that it damages the fragile motion sensor. You don't want lab fees to rise any more than they already have. Open the Data Studio software and indicate by clicking on the virtual plug at the left that a motion sensor is being used. Set the motion sensor sample rate to 50 Hz. Use sample options to set the stop time to 3 seconds. Push the start button and give the cart a reasonably fast push away from the motion sensor. You may need to tilt the motion sensor a bit to make sure that it can see the cart the entire way. Let the cart bounce off the end stopper and return. Drag and drop the graph icon from the lower left displays area onto the position icon above. Drag and drop the graph 1 icon onto the velocity icon above. In this way, both graphs of position and velocity will be lined up with the same time axis. Here's typical data for position versus time above and velocity versus time below. When the cart is moving away from the motion sensor, the position increases with time. The slope and velocity are both positive. However, when the cart is returning, the position decreases with time with a negative slope and velocity. One trick you should learn early on in your lab experience is the ability to delete data runs that are flawed. Click on Experiment in the menu and choose Delete All Data Runs. In this lab and others, you will have experimental data and wish to fit a straight line. The procedure is called linear regression. In a linear fit, the computer varies the values of both m and b to minimize the differences between the data points and the model's straight line. The error in the slope is also determined with the linear fit. The slope could potentially be as large as m plus the error. The slope could be as small as m minus delta m, the error. The slope is uncertain by an amount delta m. When the velocity is constant, we expect a flat line for velocity versus time. Yet one expects variation in any real experimental data. The mean gives us a reasonable measurement of velocity in this case, yet there is variation. The values could be as large as the mean plus 1 standard deviation, and as small as the mean minus 1 standard deviation. The value of the velocity could be considered the mean plus or minus 1 standard deviation. The laws of statistics suggest that if you measured the velocity at any of those instants of time, you could expect to be within plus or minus 1 standard deviation of the mean value about 2/3 of the time. This is the same rule that approximates that 2/3 of all pre-medical students will score within plus or minus 1 standard deviation of the mean score on the MCAT exams. Highlight a linear region of the position graph with positive slope and perform a linear fit using the Fit menu button. Record the slope m along with its error. Highlight the corresponding velocity data below and click on the Statistics button, shaped like the Greek letter sigma, to record the mean and standard deviation of velocity. Both the slope of the linear fit of position and the mean of velocity data should be similar. By comparing the error in slope with the standard deviation from the velocity mean, you can determine which approach is more accurate. Another software tool you may wish to internalize early in the lab semester is how to increase the accuracy of the displayed digits. Simply double-click on the velocity data at the upper left of the window and change the numerical display to show more digits beyond the decimal. Using the XY tool, you can identify the X and Y values of any point on your graphs. Here we use it to find the beginning time and position of our cart. Please note the ordered pair shows time first and position second. We then determine the ending time and position by moving the XY tool. From these 2 points, we can determine an approximation for the velocity by dividing the difference in position by the difference in time. All of the analysis carried out on the cart retreating from the motion sensor may be repeated for the negatively sloped approaching cart with negative velocity. Let's use the same data to distinguish the difference between speed and velocity. Now, average speed is defined as the total distance traveled divided by the total time that transpires. Thus, a cart passing a certain point, traveling to the end of the cart and returning to the same point, has an average speed given by twice the one-way distance divided by the time interval. Average velocity, on the other hand, is defined as the change in the vector displacement divided by the change in time. If the cart returns to its starting point, the change in displacement is 0, and the average velocity is thus 0. A NASCAR driver may have an average speed of 230 miles per hour, but his average velocity will be 0. Place your XY tool at the 50 centimeter mark for the cart traveling away, and then drag the corner of the box to the right until it reaches 50 centimeters for the return trip. Drag the corner of the box upward until it reaches the maximum distance. The resulting rectangle gives both distance and time. The distance will need to be doubled to get the average speed. Determine the average velocity by dragging to select the corresponding velocity data below and recording the mean. An appropriate estimate of the error in your average velocity experiment is to compare the nearly zero average velocity with the average speed and convert to a percentage.